Welcome back. So today we're going to finish this first chapter that is of rather combinatorial nature. So remember, we're trying to find the perfect maximal matching in a graph. And today I'm going to deal with the bipartite case, the so-called Hungarian method. Okay, so let us fix bipartite graph. And a matching on G. Okay, let W1, respectively B1, denote the vertices in W, respectively B, not covered by M. And now we want to consider some forest. So let F be a maximal forest. Forest is a disjoint union of trees. So disjoint union of trees with the following properties. So I have two properties. First, so the first one is that every black vertex of the forest has degree 2 in F, and one of the adjacent edges is in M. And the second property is that every tree, every component of F contains an element of W1. Okay. So I'll just make a couple of remarks, and then you'll understand why we introduced this. So the first remark is that, so this implies that W1 is in the vertices of the forest. Why? Well, we want this forest to be maximal, so if we had an element that was not in a forest, an element not covered like this, we could just add it as a singleton. Okay, that would be a tree. So otherwise, just add the element of W1 as a singleton. Second, and this is now the picture that we'll have to try to keep in mind. I will just need some color. Such a So that's called a Hungarian forest. Such a Hungarian forest can be obtained as follows. And this is called a breadth-first search. So you can do it as follows. First, you take an element of W1. So it means you take an element that is not covered by your matching. Okay? And this is how it gets tricky for whites and blacks. So you take a white element that is not covered. Okay. And then you look at all the black vertices that are adjacent to it and that are covered by M. So B in B, B adjacent to W, B covered by M. Okay, then you take the corresponding edge. So this is, the blue parts are in M. And you find yourself again with white vertices. And then you continue the same. Then you look at all the black vertices that are adjacent, that are not yet, that have not been found yet, and that are covered with M. So I don't know, here maybe I go like this. Maybe here I stop. Maybe here I have two more. Okay? And you just do this for every white vertex not covered. Right? Okay, and the lemma now that I'm going to state is basically telling us, well, if you do this, you're gonna find an M augmenting path if there is one. Okay, remember this notion of M augmenting path? So, but I'm going to state it in a little bit different way. So M is a maximal matching if and only if no element of B1, remember, so the black vertex is not covered by M, no element of B1 is adjacent to an element of B of F. Okay. So I'm just going to keep these two properties here as long as I can. Okay, that's the lemma. And here's the proof. So one direction is obvious, is that, so it's from left to right. So by way of contraposition, let's assume that there is an element of B1 which is adjacent to an element here. So let me maybe draw it here. So let's assume that here at some point I reach, so I have my maximal forest, and actually I have an element, a black vertex here, which is adjacent to element here. Okay? So what do I get? Now I look at the path which starts here and ends here, and you see that this is an M augmenting path, right? So I'll remove this and write it here. So if there exists a B in B1 adjacent to an element of V of F, this gives an M augmenting path. And remember last time the story, if you have an M augmenting path, then it means that you can indeed augment M along this by switching the edges along this path. So your matching is not maximal, right? You can augment it. So M is not maximal. Okay, so let's try to prove the other direction, which is a non-trivial one. So we're going to assume that no element of B1 is adjacent to an element of V of F. So let us assume that no element of B1 is adjacent to an element of V of F, and let us show that M is maximal. That in such a case, M is maximal. You see, again, one could rephrase this as saying, if there is an M augmenting path, then you find it by this algorithm, okay? Okay, so let's set X to be. So I'm going to take the white vertices that are not in F and Y to be the black vertices that are in F. Okay. First point, M covers X. Why is this? Well, this is because of remark 1 up there. Right, so right, if you have a white vertex that is not in F and is covered. Okay. And M covers Y. Because of what? Well, it's because of this point 1 here. Okay, every B here is covered by M in particular because of point 1, which I can now erase. So what do we have? M covers the union of X of NY. Okay, now I'm going to check that. Okay, so assume that, so if there is an edge XY in M with Y in Y, then what happens? So it means I have an edge here with Y, a black vertex in F. Well, by point 1 that I just erased, then it's this black vertex here is linked by this edge of M to an element which is in F. So it means that this means that small x is not in X, right? Is in F, so not in X. Means that, so by point 1, this means that X is not in X. Okay, so M covers X and Y, but you never have an edge of M with X in X and Y in Y. Okay. So these 2 points, these 2 points show that we have an injective map from X union Y in M given by V goes to the edge of M covering it. Right? So we have that the number of elements here is less or equal to the number of elements here. Okay. We're not completely done, but almost. So what is the next point? So I claim now that X union Y is a point cover of G, which means it meets every edge of G. Okay. And so maybe I'm just going to start in brackets with saying that this gives the claim. So this shows, this completes the proof. Indeed, if M prime is any matching of G, then the number of elements in M prime is less or equal to the number of elements of any point cover. And this is an exercise in the homework sheet. It's numbered exercise 2 of this third homework assignment, which is here. And we had just checked that this is less or equal to the number of elements in M. So it means that M is maximal. Which is what we wanted to check. So now we have to see that it's a point cover, so it meets every edge. Okay, so let's assume that we have some edge WB not covered by X union Y, with W being white and B being black, and we look for a contradiction. Okay, so let's think. We assume that WB is not covered by X union Y. So it means that W is not in X and B is not in Y, which means that W is in V of F and B is not in V of F. Okay. Now, by our hypothesis, which we have not used yet, the hypothesis is we have no element of B1 adjacent to an element of V of F. But here we have an element B, which is adjacent to an element of V of F. So, by hypothesis, B is not in B1. Okay, since it is adjacent to W, which is in V of F. B not being in B1, this means that B is covered. Is covered by M. Okay, so the picture is we have W, which is adjacent to B, which is covered by M. Giving W prime. And so we have that W is in V of F, and B is not. V of F. Okay, here it could be, we could think maybe W could be equal to W prime, but this is not possible. Why? So W, note that W prime is not equal to W, since what? Well, whenever a wide vertex in the forest is adjacent by an edge of M, then it's adjacent to an element which is again in the forest. Since so I'll just make a drawing, if I have W M B and W in V of F, this would imply that B is also in V of F. So what do we have? We have this picture here. We have this vertex which is in the forest, and then we have this one which is not in the forest. So do you see the contradiction? Here, actually, it means that we could add this to the forest, and this contradicts the maximality of the forest. So F prime equal to F union WB union BW prime is a bigger forest, is a bigger Hungarian forest. Okay, this was a slightly lengthy argument to show that this algorithm works. So maybe I'm just going to repeat or make some remarks on what we have proven. So let's take this as remarks. First remark, so this lemma really shows, as I said already, that this algorithm, this breadth first search algorithm, meaning you start with all, so you take a matching, then you fix all the white vertices that are not covered, and you start building this forest like this. And you just go as far as you can. It means that this will find an M augmenting path if there is one. Okay. We'll find and then what you do, you have, so if you have not found any means if you have a maximal matching, you're happy. If you find one, then you take this M augmenting path, you exchange the edges along this M augmenting path, and then you run again the algorithm. Okay. And so the running time is, so maybe just, so this algorithm is due to Kuhn in 1957. And it can run in big O of n cube operation. And the number of vertices of the graph. And I'm not saying this is a record. Most probably it can be quicker. Okay, so I wonder if I want to give you a stupid or didactic example. Not yet, maybe let's just make an example. And you're going to have another one in homeworks. See also homework 3, exercise 3. So I'm drawing a bipartite structure on 2x4 square lattice, and let me draw a matching that is not maximal. Okay. Okay, so these are the edges of my matching. And okay, so I start with W here in W1. Okay? So first step, I go to the neighboring ones. And maybe I'm just going to say, okay, these are at level 1, okay, in the tree as I progress. This one is also at level 1. Okay, and then next step, I look at these adjacent, so these elements of M, and I find myself here at level 2, here at level 2. Okay, then I continue, I go here, level 3, here, level 3, and here, level 3. Next step, this one, so I'm at level 4 here, level 4 here, and level 4 here. Okay, here I have to stop. And here you see, well, for example, here I can continue here. Well, okay, let's say here I have my maximal forest. Here it's a tree. Okay, it's what I've drawn here. And I do have a B in B1, which is adjacent to these elements here. So now I can, for example, I consider this edge here, and I have my m augmenting path, which is here. Okay, so I get the m augmenting path, which has the form here. Up. Okay, and then I switch. So I switch the edges of M along this path, and what do I get? So here I have the same, here the same, here the same, and I switch them along this path, and I get this, and this one is a perfect matching. Okay? Summary. On the bipartite graph, we have a polynomial time algorithm to find explicitly a maximal matching. Okay. I'm going to come to the general case, and here I'm not going to be precise. I'm not going to give you all the details. So the general case Edmunds algorithm. So it's only in 1967 that there was a general algorithm that was found. So this algorithm was found by Jack Edmunds in 1967. So we will not give, many details here. That just explain a little bit the idea. What can go wrong in the general case? What can go wrong if we try the same algorithm, okay? So I'm just going to make, again, a didactic or a slightly stupid example. So let's assume we have the following situation. So here is my graph. And here is my matching. And you say, okay, I'm going to do the same thing. So I start here. Okay, why not? That's an uncovered vertex. And you start looking. You start your search the same way, okay? Well, you start. What do you have? You look at the neighboring vertex. And then this. Then you have that. And then basically you're stuck there. You're stuck there, and you have failed to find the M augmenting path. There is an M augmenting path. It's, for example, here, here. This one. You see, the trouble is here that there is a structure here which never occurs in the bipartite case, that's a cycle of odd length to start with, okay? You never have this, of course, in the bipartite case. Here you have it, and basically you're stuck. So the problem is that during the search, you encounter subgraphs of the following forms. Subgraphs of the form. So it's a cycle of odd length where the matching alternates except at one point, which Edmunds called blossoms. And this whole algorithm of Edmunds is called the blossom algorithm. But now here is the miracle, actually. So again, I'm not going to prove anything, so the miracle lies in the following fact, which is easy to prove using Berge's theorem. So here's the fact. Let M be a matching in G, and let B, I already have letters B, it's okay, be a blossom. So blossom relative to M, meaning this form. Let G prime be the graph G with B shrunk to a vertex, and let M prime be M without the edges of B. And the statement is then M prime is a maximal matching in G prime if and only if M is a maximal matching in G. And so now, therefore, there is the following algorithm. Again, I'm not going to prove anything. So hence, we have the following algorithm. So basically, you do the same algorithm as in the Hungarian method. So for each V not covered by M, construct a maximal so-called M alternating tree. So something like what we had before, simply we don't have a bipartite structure anymore. okay, etc. So you build this maximal structure, and then what can be checked is that if you do this, then either this will lead to an n augmenting path, so typically this would happen if you have another tree that comes like this, and you have two blue edges, the end of two blue edges that can be linked, then you will find an augmenting path by going through these two. So either this will lead to an augmenting or to a blossom. In the later case, you shrink the blossom and you continue. So if you found an augmenting path, you're happy, you just change everything along this path and you run it again. If you find a blossom, you shrink the blossom and you run on the graph where you have shrunk the blossom. In the later case, shrink the blossom and continue. And so it's a fact that this, I'm not going to prove it, it's a fact that this works. And so it's a fact, so again, I'm going to state this as two facts. So every n augmenting path can be found in this way. And second fact, this algorithm can run in big O of t squared times number of edges. Okay, so this was just a very short survey of the general case. And now I'm just gonna state, basically introduce the next section and then make the break. So it's section 1.3. How can we count, or can we count perfect matchings on an abstract graph? So we answered positively all the questions so far. Can you tell whether a graph has a perfect matching? Yes. Can you actually give yourself one if there is one? Yes, you can do better. You can actually give yourself a maximal matching, and okay, then you can tell whether it's perfect or not. You can do all of this in polynomial time, no problem. So now the question is, can you actually count the number of perfect matchings in an efficient way? And so in general, the answer will be no. But we can still give some estimates. And this will be the subject of the first paragraph of this last section. It will be about the permanent of a matrix. So what I'm going to do in 15 minutes, I'm going to define the permanent of a matrix and then explain that actually sometimes you have some estimates on the permanent of a matrix. This will lead to upper and lower bounds on the number of perfect matchings on a bipartite regular graph, for example. And then we're going to address the question in general, can you actually count the number of perfect? And then I'm going to just state the fact that no, you cannot. And basically that's going to be the end of the class of this week. Next week it's going to be about explaining that all hope is not lost because of this. Okay, let's make the break. Okay, maybe I'll just come back to this discussion. I had two questions, two people asking me the same question, which is a good question. So here, you see, not only if you have M prime is a maximum matching in G prime, if only if M is a maximum matching in G, but on top of that, if you find an M prime augmenting path here, it uniquely determines an M augmenting path here. So maybe let me just, so we had this example here. So we had this example, so we had started here, and okay, we find a blossom. That's a blossom here. Okay, so you shrink it, and you get, so that's G and M, and you shrink it, and you find M prime in G prime, which is like this. Okay, this is an M augmenting path, right? So you remember it, and then you look up here, and what do you have? You have this edge here, you have this edge here, and you have this edge there, and you see that there is a unique way to go in the blossom. You just go through this direction here to find an M augmenting path for G, and it's this thing here. So I should have said this before. Not only you know that you have a perfect matching if and only if, but actually what you're looking for, that is the M augmenting path, you don't lose any information when you shrink the blossoms. Okay, maybe that's a little bit more clear. Okay. So now, counting perfect matchings. So let A be an n times m square matrix. Square matrix. Definition. The permanent of A is defined as the sum over all permutation of an object of A1 sigma 1, A2 sigma 2, An sigma n. Okay, now recall that if G is a bipartite graph, with numbered vertices, so it's W1, Wn, B equal B1, Bn. Then one can form the associated bi-adjacency matrix by setting, so A is Aij, and we set Aij equal to 1 if, let me just see my conventions, so Bi is adjacent to Wj and 0 else. Okay, we had already defined this. Simply, we had seen a weighted version, but okay, that's just the unweighted version. And more so that's if the graph is simple, and if the graph is not simple, you just set here you set the number of edges. Okay, so or Aij equal the number of edges between Bi and Wj in general, meaning if the graph is not simple. Well, now let's try to compute this permanent. So the permanent of this matrix is so you see, if let's assume that the graph is simple, but it works in general, but so what do we get? If this permutation sigma is actually supported by a perfect matching, okay, meaning there is an edge between 1 and sigma 1, there is an edge between 2 and sigma 2, between n and sigma n, then we'll have a 1 here. This will be 1. If this permutation is not supported by a perfect matching, we have 0. So what do we have here? We have a sum over all perfect matchings on the graph of 1. So we have the number of perfect matchings. So it means that actually if you want to compute the number of perfect matchings on a graph, you just, with many quotation marks, need to compute the permanent of a matrix. So to compute the number of matchings with G bipartite, and let's say n simple, we only need to be able to compute the permanent of compute efficiently, or to compute the permanent of a matrix with A, which has, well, if the graph is simple, it's a matrix that has only entries 0s and 1s, okay? With a so-called 0-1 matrix, i.e. all entries are 0s and 1s. Right? So of course there is hope, because this permanent looks very much like a determinant. Obviously, you have this just a sign. So since the determinant of A, which is almost the same as the permanent, you only have. And here, so I think I used another convention last time. So I want to look at the signature of a permutation as plus or minus 1, okay, not 0 and 1. Okay, this is just a convention that I might mess up along the way. So just remember, for us the convention will be that it's plus and minus 1. Since the determinant looks very much the same, in general, the determinant is this. But obviously, this sign messes up everything, right, in general. So here, you might say, OK, so why not just, OK, the permanent might be difficult to compute, but OK, let's try with the determinant. But obviously, if you look at the determinant of your bi-adjacency matrix, you'll have these signs which will have cancellations of the perfect matchings, and you will not end up with this in general. OK, so it's easy to compute you all know that by Gauss algorithm, for example, you can compute this in O(n) cube operations. But on the other hand, the signs mess up everything, mess up the count in general. So in general, you cannot consider the determinant, but then the question is, okay, but maybe actually there is also some kind of permanent calculus. You know, we have a determinant calculus. It's a very efficient way to compute a determinant. Well, is there the same for a permanent? You know, so there is. Okay, so the hope is that there is a similar, well, simply a permanent calculus. Okay, we'll see there is none, but for starters, for a start, let us give bounds on this permanent and use them to get bounds on the number of perfect matchings. Okay. Okay. So I'm going to state these bounds without proof. It's the first theorem, which is the so-called van der Waerden conjecture. Which van der Waerden stated in 1926, which was proved by Falikman and Egorichev in 1981. So here's the theorem. Let A be a doubly stochastic matrix, which means that we have non-negative entries all rows and columns sum up to 1. Then you have an inequality, then the permanent of this matrix is greater or equal to n factorial over n to the power n with equality if and only if all the coefficients are 1 over n. Okay, so that's a lower bound, and I'm going to state a second theorem, which will give an upper bound. So this one is the so-called Mink conjecture. So Mink's conjecture, which was stated in 1967, which was proven by Bregman in 1973. And here it is. So let A be a 0-1 matrix. With rows sums R1, Rn. Then the permanent of the matrix is less or equal to R1 factorial R1 over R1, etc. Rn factorial 1 over Rn. And I think it's fair to say that the difficulty of these results are measured by the time it took between the conjecture and the actual proof. So this one was really quite an achievement. Nowadays you have some relatively easy proofs apparently. This one, now you can find proofs that are like 2 pages long. Okay, but of course I'm not gonna prove this, but let me use them for a corollary. For our perfect matchings, so if G is a simple bipartite K regular graph, then the number of perfect matchings is, we have the following bounds. Okay. Let's give the proof. So, let G be a simple bipartite K regular graph. And let A be its bi-adjacency matrix. Then, so the number of perfect matchings in M is equal to the permanent of A. And now what I want to do is I want to use this. So I want to change A to a doubly stochastic matrix. So in my matrix A, all the columns and lines, they sum up to K, right? So the graph is K regular. So here what I can do is I can take out K to the power n. Okay, you think about it, so you divide every coefficient by K here. So you have times the permanent of 1 over K times A, right? So this is simply because the permanent is homogeneous of degree n. And now you see that this matrix here now is doubly stochastic. So now this is a doubly stochastic matrix. So you can apply Vandal conjecture. So this is greater or equal to, all right, and this is indeed the lower bound we're looking for. Okay? Okay, on the other hand, we will now apply Mink's conjecture, and here we'll use the fact that G is simple. So here, let me just note that here we did not use, so this bound holds even if G is not simple, we did not use that G is simple. But here now we will use it, so permanent of A. A now, since G is simple, A is a 0-1 matrix, so 0-1 matrix since G is simple. And so this is less or equal to, so each of the rows sum up to K, so we have K factorial to the power 1 over K power n, and this is the bound we wanted, right? Okay, so I'm just going to make a couple of remarks. The first remark is that I wanted to make a discussion on how sharp these bounds are, but I put it in the homework. So see homework number 3, exercise 5, I think, right, for a discussion of the sharpness of these bounds. I'm going to keep this. Second remark. So now we're going to play a really funny game. So what we will do, we're going to assume that k, we're going to fix k, and we're going to take n to, we're going to take the limit in n. Okay? So now let us fix k and take n to the limit as n goes to infinity using Stirling's formula. Okay? So maybe I'm not going to write the details. I mean, it's a very easy computation. So again, what I use, so Stirling formula, I use it in the following form. Maybe there are several forms. So n factorial is square root 2 pi n over e or n times r of n with r of n going to 1 as n goes to infinity. Okay, you just plug in, so you take this inequality and you replace n factorial with this and you take logarithm, and what do we get? We get the following, 1/2 log of k minus 1 is less or equal to the limit as n goes to infinity of 1 over 2n log the number of perfect matchings less or equal to log of k factorial over 2k. Okay. So this thing here, you will see it many times in the future. So this is called the free energy of the model. I'm not saying that this limit always exists, but if it exists, it's between these two. So let's make a couple of examples. So for example, consider the square. So let's say, I want to make an example with k equals 4. So what can I have as a bipartite 4 regular graph? So, well, some square lattice. If you have a square lattice, you have problems at the boundaries, right? So what you do is you're going to take a square lattice, but that is periodic, okay? You embed it on the torus, okay? And then you might have bipartite issues. So you need a square lattice that is even in both directions. In this case, right? Here. So consider the 2m by 2m square lattice. So topologists say in the torus, people in statistical mechanics say with periodic boundary conditions. So let's say with periodic boundary conditions. I hope you understand what this means. So i.e. on the torus. So, and now let's look at this limit. So, I'm sorry. So here it's k-regular graph with 2n vertices. Sorry about that. of course, I mean, you had understood it because it appears in the proof, but okay, I want to state it. Well, so this is a simple bipartite for regular graph. So this limit, if it exists, so limit as, so I'm going to say as m goes to infinity of 1 over, so here I have 4m squared, okay, that's the number of vertices in my graph, log the number of, here, is in between these two where k equals 4, okay? So I'm going to tell you what we get. So we get, here 0.193 something, and here 0.38. Now here's the amazing thing. In 2 weeks, we're going to compute this number exactly. So in 2 weeks, we will see that actually this number is g over pi, where g is Catalan's constant. That is 1 minus 3 plus 5 minus 7 is Catalan's constant. And this is equal to, let's check at least that we're, so it's 0.2916. Okay. Another example. Is the, let's say again, biperiodic, so periodic hexagonal lattice. So it means it's k equals 3. So this gives the bounds. So you just replace by k equals 3, and what do you get? Here you get 0.05 less or equal to your number, which is less or equal to 0.28, etc. Again, we will compute the actual, the exact value. So of course, this is kind of a teaser for the rest of the class. And I'll end this with one last remark, so it is the third remark. So now we can take this formula and actually use Stirling again for k factorial, okay? So using Stirling for k factorial, we get, again, I'm not gonna give the detail, but it's easy. So we get that the limit as n and k goes to infinity of 1 over k nth root of the number of perfect matchings equal to 1 over e. Which I find very funny. So you take your family of k regular graphs with 2n vertices, and you have and you look as k and n go to infinity, and the number, to some extent, the number of perfect matching is very stable. Well, let's see. Okay. And now in the last 15 minutes, I'm just going to state again without proof variance theorem. So now we had some bounds on this permanent, but okay, maybe actually it doesn't tell us, maybe actually it's possible to compute it efficiently, right? So, but what about the exact value? The exact value for this number. So again, we will not give many details. Okay, so let us recall some terminology of complexity theory. Okay, since the answer to this question, can we count it efficiently, is negative, you need some complexity theory to tell you, well, okay, it's negative because it's of such and such complexity. Okay, so. So the first terminology that I had already, so a decision problem is in the class NP if it can be answered by a non-deterministic Turing machine in polynomial time. Meaning the machine guesses the answer and then it checks it in polynomial time, okay? Equivalently, we can say, so that's the terminology, so a non-deterministic Turing machine provides so this is called an accepting computational path. Okay, meaning, well, okay. Right, and so now here's the new terminology of that we'll need here. It's actually a terminology that was introduced by Valiant when he proved the theorem I'm going to tell you about. Now we're not going to look at decision problems anymore, right? But we're going to look at counting problems. So a counting problem is in the complexity class sharp P if it can be given by counting the number of accepting computation path of a non-deterministic Turing machine. So before continuing, let me give an example. Well, counting the number of perfect matchings on the graph is in sharp P. Okay, so this is a positive result. Why? Since since we know that that to check, you have a non-deterministic Turing machine can check in polynomial time. You can non-deterministic Turing machine can guess a perfect matching and then check that it is a perfect matching in polynomial time. Okay, since giving yourself a perfect matching is in NP. So this is something that is positive. Now, a counting problem is in the class sharp P complete if it is in sharp P and every counting problem in sharp P can be reduced to it. So if you tell yourself that a counting problem is sharp P complete, that's rather bad, right? So in sharp P it's positive. If it's in sharp P complete, it's bad because it means that every problem of this form, if you're able to solve it efficiently, you can solve any problem of this form efficiently. Okay. So here we know that counting perfect matchings is in sharp P. That's basically because of Tute's theorem. But since Tute we have proved some other theorem. We have proved that, well, actually, giving a perfect matching, it's not in NP, it's in P, actually. So one might think, okay, actually, since I have a polynomial time algorithm to give myself a perfect matching, then surely I'm not going to be sharp P complete when counting them, right? And this is the amazing thing, is that actually it is sharp P complete, counting perfect matchings. So let me just give you first a couple of examples. Counting the number of k colorings of a graph is sharp P complete. Another example, counting the number of so-called linear extensions of a partial order on a set. So linear extension of a partial order, it means the way you can extend a partial order by a total order. So it means a total order extending it is sharp P complete. Now here's the theorem by Valiant in the 70s, 1979. Computing the permanent of a 0-1 matrix is sharp P complete. Corollary, counting the number of perfect matchings on a simple bipartite graph is sharply complete. So even in the bipartite simple case, it's already hopeless. Okay. So maybe as a remark, so this is I don't know so much about complexity theory, but apparently this class of problem is extremely interesting because it's a problem where the actual search problem, the SCA search problem, can you find a perfect matching, is in P, but the counting problem is sharply complete, right? So it is remarkable that the counting problem is sharp P complete, even, let's say, and the associated searching problem is in P, which we know by the Hungarian method and Edmunds algorithm, let's say by Edmunds algorithm. So this theorem implies that there is no hope to find a polynomial time algorithm to count the number of perfect matchings in general. Why? So it doesn't mean that, it doesn't mean it's impossible, but if you find one, that's one of the biggest surprises in modern day mathematics, basically. Because if you find one, it means in particular, so if you're able to count this efficiently, in polynomial time you can count it. Well, in particular, it means in polynomial time you can say whether it's 0 or 1. So it means in polynomial time you can solve any NP, since it's sharp P complete, you can solve any MP complete problem, any NP problem. So it implies that P equals NP. Ready? So if you find a polynomial time algorithm to compute the number of perfect matchings on any graph, it's a much stronger result than P equals NP, which would be already kind of a surprise, right? So indeed, such an algorithm would would imply, in particular, that any NP problem is actually in P. So that's the famous P equal NP thing. So again, I'm not saying it doesn't exist, but don't try looking for one, let's say. I think that's all I wanted to say in today's class. So I'm just gonna, again, so why are we not stopping the class now? Why can we still go on and say something interesting? It's because of there is no hope to find polynomial time for this in general. But actually, you might say, yeah, okay, so now let's forget about the general combinatorial question. It's too hard. But maybe you can for some class of graphs, maybe it's possible, right? And this is the case. And actually, that's going to be, so that's the end of chapter 1 about perfect matchings on abstract graphs. And from now on, we're going to basically embed our graphs in the plane or in surfaces in general. And the summary of chapter 2, which is going to last for maybe 4 weeks, is, well, actually, if you restrict yourself to graphs that are planar, for example, then you have an efficient algorithm. It works. More generally, if you restrict yourself to graphs of a fixed genus or a bounded genus, let's say, meaning, so the genus of a graph is the minimal genus of a surface in which your graph embeds. So let's say, asking for a general case is too much, but maybe, for example, I want to look at all the graphs that are planar and on the torus, right? We saw a graph on the torus. We want to look at the square lattice, for example, and square lattice on the torus. Okay, so it's a bounded genus 0 or 1. Then you have a polynomial town algorithm. In general, if you bound your genus, you say, I want any graph up to genus 27, you can have a polynomial town algorithm. Okay. But of course, now it's gonna, I'm talking about graphs in surfaces, so we're gonna change a little bit the tools we're using. So until now, it was only combinatorics, basically, a little bit of linear algebra. And from now on, we're gonna look at graphs in surfaces, and this will mean that we're gonna still use linear algebra, but we're going to use also tools of topology. So in the summary of the class, I had said I'm going to focus on the amazing variety of tools that are coming into play in the study of this model. Now I'm done with the combinatorial tools, basically. And chapter 2 is going to be with tools of topology, let's say. And we're going to see in chapter 3 that we also have tools of algebraic geometry that are going to come into play. Okay? Have a nice week. See you next week.